we're going to be talking about improper integrals. And there are two types of improper integrals. We're first going to address type 1, which is when the interval of integration is infinite. So first let's consider the integral from 1 to 2 of 1 over x squared dx. And we know if we compute this definite integral, we would have the area under the curve here between 1 and 2. And we can figure out the antiderivative, which would be negative 1 over x, and then evaluate that from 1 to 2 and have negative 1/2 plus 1. So this area under the curve is 1/2. Now, instead of 2, we could let b be any number greater than 1, and how that would change is our upper limit would be b. When we evaluate, it would also have a b, and so we'd have negative 1 over b plus 1. And then for any given b greater than 1, say for example 5, I would know the area under the curve, if b equals 5, would be negative 1/5 plus 1, or 4/5, and I could continue to do this for any b greater than 1. But what happens to the area under the curve as b goes to infinity? So as we consider this, we're going larger and larger and larger here, and as if we want to go to infinity, what we could do is we could take the limit as b approaches infinity, 1 to b, 1 over x squared dx, and we had already computed this integral. So now if we apply the limit, if I'm looking at this fraction, the numerator is fixed at 1 and the denominator is becoming larger and larger, so we know that fraction goes to 0, and so this limit equals 1. Therefore this integral equals 1. Well, what does that tell me then? It tells me the area under the curve of this function from 1 to infinity equals a finite value. It equals 1. Let's summarize what we would be doing for these type 1 integrals then, improper integrals with infinite bounds. The case we just looked at, we have a continuous function, closed interval from a to infinity. So if we wanted to compute this integral and the upper limit was infinity, we would put the upper limit to be b and then take the limit as b goes to infinity. Now we can do an analogous thing on the other side. So if we looked at a continuous function on the interval from negative infinity up to and including b, then if we wanted to compute negative infinity to b, we would replace the negative infinity with a and take the limit as a approaches negative infinity, and we would be able to then see if this limit exists. And if the limit exists, then we would have this finite value. Okay, there's one last case then. What if we wanted to integrate from negative infinity to infinity? So we're looking at both ends, looking at this interval from negative infinity to infinity. So then we would let c be any real number, so we just arbitrarily could choose a c here, and we could actually split this up then into two pieces, because we know when we have an integral on an interval, we could split the interval up, and we could look from negative infinity to c, and then from c to infinity. And so we would do that and replace these negative infinity and infinity limits with a and b here, and then take the limits. Now it's down to, this is like part b, we'd know how to work that, and then part A on the last slide, and so we could work both of those pieces and then sum those together if the limits exist. So in each case, if the limit exists, we say the improper integral is said to converge, and we'd get some finite value. If it doesn't exist, then we just say that this improper interval diverges. And these are going to be important words that we want to know. We're going to be referring to them several different times later in the course. So converge, the limit exists, we get some finite number. And if the limit does not exist, then we say that this integral diverges. So let's consider looking from 1 to infinity of 1 over x to the p dx. Does this integral converge or diverge? Well, we just did an example where we had the p being 2, we had 1 over x squared, and we found that it converged to 1. But I hope you say, as you get thinking about this, it depends on what the p is. So let's consider this for a minute, and we're going to look at 1 over n to the p, where n is an integer, just so we can kind of study what the effect of p is on something like this. I'm going to use an interactive applet that's found at mathopenref.com/calcseries.html. HTML, and I'll post this link later, so if you want to go play with this, you can. So let's see what we've got here. So here we are looking at n rectangles, and we are going to sum those up. And you can see here then n is our number of rectangles. S sub n is the area of the nth rectangle, the last rectangle, and then capital S sub n is their sum. So we're looking at 1 over n to the p, and we've got 10 rectangles showing in our picture here, and p here is -1. Now we can see that the sum, it just keeps growing. These are the dots here. This is the dots represent the sum, and it just keeps getting larger and larger and larger. So when we have our 1 over n to the p, the sum of that is not going to converge. It's going to diverge. It's just going to keep getting larger and larger. And if we went more negative, that would get even worse. Think about it, it's because if we had 1 over n raised to this negative exponent, essentially you could move that to the numerator, and if p was initially negative, it would become positive, and this thing would grow exponentially. Now what would happen if we vary p and we get it closer to 0? We see as we are still negative but closer to 0 that that sum is getting smaller. Our rectangles aren't as large as they were, but it still is increasing here. Let's go ahead and change p more. And what happens if we had p equaling 0? Actually, I'm going to type in 0 so we can hit it right on. If p equals 0, what are we seeing here? Well, we would have 1 over n to the 0, and n to the 0 is 1, so we would just have 1 over 1. You can see that each term is 1. If we sum up 10 terms, we get 10, 50 terms, we get 50, so this is just increasing linearly here. Now, what's going to happen if we make p positive? We'll first go with just a little positive number. We're trying to determine if this sum converges to a finite number or if it just keeps getting larger and larger and larger. As we look here, can't quite tell looking at the graph, these rectangles are quite small. As we look here at the sum though, we can see that the sum is still increasing, increasing, increasing. Let's make p a little bit larger. And now let's go ahead and see what the sum is doing, and maybe what we need to do is change our y max so we can see what's going on here a little better. We'll make it 10. Alright, that helps us see our rectangles better, and we see that these dots which represent our sum look to be still on a continually increasing curve, and as we look at the actual numbers, that is what it appears to be doing. Let's go ahead and make it a little bit larger. And now as I'm looking at it, p is now 1.51, and as I'm looking it looks to be increasing, but maybe it's increasing but staying under a limit, staying under 3. As I can see it is increasing at a much slower rate and possibly has a limit there. Let's let p get a little bit bigger. And looking for what p being 2.2, look at this sum as I continue adding terms. I didn't go above 1.5, and I've added up 5,000 terms, and I am still below 1.5. This appears like it might be approaching 1.5. Let's let our y max be 1.6 and see how that looks. And it looks to me like it's leveling off. You can't tell just simply by looking, but that'll give us an intuitive sense for what we might expect, and then we're going to go algebraically and using some calculus figure this out. So what did we kind of see? Negative p-values definitely diverged. Very small positive p-values look like they also diverged, but at some point as we increase the p-values, and it looks like when we hit about 1 or 2, it looks like they're starting to converge. Let's get an even larger p-value, and for this particular one it looks like it won't go above 1.15. Looks very much like it is converging or has a finite limit. So let's go back and look at this a little closer. What if we go ahead and compute this integral? So we're going to take the limit as b approaches infinity, integrating from 1 to b, and we'll express this as x to the negative p, so we can think of the integration here and using the power rule. So when we integrate this, we're going to need to have one higher power, so there'll be a plus 1 added here, and then we'll need to multiply by the reciprocal of that power. So we still have our limit as b goes to infinity. Here is the reciprocal of our power, and then here is one higher power, and we need to evaluate this from 1 to b. So substituting in those limits, we have this. Now let's have a look here. Looking at this piece, p will be fixed. We will determine a p. It will be a constant. So everything in this piece is a constant. So this piece will be a constant. Therefore, the limit as b goes to infinity, this part will remain constant. So that's not going to be an issue. Now, if we look at this coefficient here, same thing. This is going to be a constant because this will be for a fixed p-value. So the piece that we are interested in is this one right here. Let's go ahead and put it up here. So we've got the limit as b approaches infinity of b to the negative p plus 1. So let's think about this. This is essentially for any given b here. It's going to be an exponential, and so if this exponent is positive, it will be growing exponentially. If this exponent is negative, it will be decreasing and it will go to 0. Well, so for a p-value that is less than 1, this sum will be positive and this will diverge. It will continue growing. If the p-value is greater than 1, then this negative term is larger and we'll have b to a negative value. And then as b gets larger and larger and larger, this will go to 0. So it will converge. Now, if p actually equaled 1, let's go back and look at it right here, because if p equaled 1, we would have the integral from 1 to infinity of 1 over x dx. And that's a special case because we know the integral of 1 over x. That would be the natural log. That would be the natural log of x. And if we evaluated that from 1 to b, as we let b approach infinity, we would have the limit as b approaches infinity of the natural log of b minus the natural log of 1. And we know that the natural log of 1 is 0. And what does the natural log do as b goes to infinity? Well, I would just think of the natural log graph, and it's always increasing, so it's also going to go to infinity. So in the special case where p equals 1, that's sort of our line, but it diverges there as well. So as we look here, here is our graph when p equals 1, and that will diverge. And for any value when p is less than 1, we would have something like this red curve, and that's also going to diverge even though the function is decreasing. And then for anything where it's greater than 1, that's like our blue graph, it will converge. And so what we find as we're looking here is we need to have things, this exponent, we need to have this exponent greater than 1 for convergence. So let's sum this up. If we're looking at this integral from 1 to infinity of 1 over x to the p dx, it is convergent if p is greater than 1 and divergent if p is less than or equal to 1. This is going to be really important to us later as we study infinite series, and it tells us that if we have this continuous function and we're integrating from a to infinity, it must do more than just simply decrease to converge, it has to decrease to zero sufficiently fast, and we will be talking about this more later in the course. Going to be important. This will be called a p-series. Let's look at one more thing that can help us as a consequence of this. What if we have two functions and we know that f of x is always less than or equal to g of x, and we know that the integral from a to infinity of g of x dx converges? Because these values of f of x are always less than or equal to these values, if I know that this integral of this upper function converges on from a to infinity, so does the lower one. If we know that f of x is always less than or equal to g of x, and we know that f of x diverges, then we would also know on the same interval that this upper function, meaning that its values are always greater than or equal to this one, would also have to diverge. And these should be intuitive. We're not going to be able to prove them here, but looking graphically, that should make sense to you. That should make sense to you looking at the graph. If this function diverges on this interval and these values are always less than or equal to these function values, then this function would also diverge. So let's state these ideas formally in the direct comparison test for improper integrals. So we have two functions f and g, and they are continuous on this closed interval from a to infinity, and f of x is always greater than or equal to 0, and it's always less than or equal to g of x for all x on this interval. So if the integral from a to infinity of g of x converges, then the integral from a to infinity of f of x dx also converges. And if the integral from a to infinity of f of x dx diverges, so this is our function whose values are always less than or equal to, then the integral from a to infinity of g of x dx also diverges.